I would like to talk about what happens when the next number in a sequence is the sum of the two prior numbers. So to start off with, we'll pick two arbitrary numbers. Let's try 2 followed by a 1. So the next number will be a 3 followed by a 4 followed by a 7 followed by 11 and then 18 and so forth. And so if I want to depict that visually, I could start off with a 2 by 1 rectangle as best as I can draw it, and on the end I'll tack on a 1 by 1 square, and then I'll add to that a 3 by 3 square, and then a 4 by 4 square, and we'll continue this. Okay, and what happens is that the aspect ratio of the overall rectangle starts to change, and in fact it will converge upon a given value. So just to illustrate this, I will pick another sequence. Okay, this time I'll start off with a 1 and a 1, 1 and a 1, and the next number will be a 2 followed by a 3 followed by 5 and then 8 and then 13 and so forth. And again, we'll start off with a 1 by 1 square and add another 1 by 1 square to that. And if you notice, the aspect ratio of this rectangle here is going to change. So next I'm going to add a 2 by 2 square as best as I can do it accurately. Okay, and then a 3 by 3, and continue in the sequence here. And if you notice, both this rectangle and that one, even though we start off with two different aspect ratios, the aspect ratios, which is the length divided by the width, are now starting to look more similar. And the reason is because when taken to infinity, the aspect ratio, which also happens to be the ratio of the last number divided by the second to last, okay, converges upon a given value, and that value is what we call the golden ratio. And any such sequence where the next number in the sequence is the sum of the two prior numbers is what we call a Fibonacci sequence. Okay, so we know it converges on the golden ratio, but exactly what is this golden ratio? So the way to find out is I'm going to try to do a case where the ratio does not change, because then if I start at the right ratio, well, converging will not change it. So let's say we have a side here that's length x and a side here that is 1. Okay, so now if I had add an x by x squared to it, okay, the aspect ratio should not change. So in other words, x divided by 1 should be the same as x plus 1 divided by x. So let's go ahead and try to find out what x is. So we can say x over 1 is equal to x plus 1 over x. So now we can say by cross multiplying that x squared is equal to x plus 1, or in this case I can solve for x using either the quadratic formula or completing the squares. I'll complete the squares today. So x squared minus x is equal to 1. So I will take half of this coefficient and I will square it and add it to both sides. So coefficient is -1, so half of that is -1/2 squared. So plus minus 1 over 2 squared, which is the same as adding a quarter. So now it's x minus 1 over 2 squared is equal to 5 over 4. So now I'm going to take the square root, in which case I'm going to get a positive and negative number. I'm only interested in the positive, so I'll just take the positive square root. So x minus 1/2 is equal to the square root of 5 over 2, in which case x is equal to 1 plus the square root of 5 all divided by 2. And that is the golden ratio, which equates to around 1.618 or so. So now we're going to draw a golden ratio rectangle as best as we can. and we're going to illustrate something else. Okay, so again, I'm going to keep adding squares to it. Okay, and the beauty of this is, since the values tend to converge on that number, well, if I'm slightly inaccurate in my drawing, as long as my next attempt is a reasonable attempt to add a square to it, it should be a self-correcting mechanism that converges back to the same aspect ratio. Okay, however, the primary thing I want to illustrate is that if I were to start connecting the corners, okay, and start going out, what we wind up with is a spiral. Not just any spiral, but a spiral which we refer to as a geometric or exponential spiral. And this is actually quite common in nature, especially in the shells of creatures such as the snail or the nautilus. And the reason why is because as the animal grows, the shell in the geometric spiral allows the animal to maintain the same proportion, and not just that, but the shell will stay over the same location with respect to the center of gravity of the animal. Another case where we see a geometric spiral is if we see a moth spiral up into a light bulb accidentally, or a fly spirals down to land on the spot. It follows a geometric spiral, and the reason is because by keeping the reference point at one fixed angle with respect to its flight path, it will mathematically fly a geometric spiral until it reaches that spot. Okay, so let's see if we can illustrate that. So let's say we have a spot here, and a fly is coming into that spot at a given angle. Okay, and the angle with respect to the flight path, with the one which is not going to change, let's say that angle is called phi. And for the reference, I'm going to pick a line, okay, in a given direction, and the angle of the point that of the line between where the fly is and the reference point, and between that line, we'll just call that theta. Okay, so now, if that angle stays the same, let's say there's an instantaneous change in time, okay, which means there's a very small change in angle. Okay, we're going to go ahead and take that point, and we're going to expand that and take a closer look. Okay, now the key thing is, whenever you take a curve such as this and view it, assume it's expanded infinitely, and you take an infinitely small portion, well, the curve is going to look very much like a straight line. Okay, and the lines, the two differences in lines, they're going to look parallel in this case. Okay, so now if we were to take a line that's perpendicular to the line pointing towards the reference point, it's obviously going to form a right angle, so it would be like drawing a right triangle right here. Okay, so now we'll call the distance from the reference point r, which is the radius. Okay, and so now if this represents a very small change in position because of a very small change in time, then the difference in radius, which we'll call dr, will be represented by this right here. This angle here, this is an angle that does not change, which we call phi. Okay, and here, this distance here will be r times d theta. Well, you have the change in the theta, but the further out you are, the further apart those will be, so that's why it's r d theta. Well, now, if phi is constant, well, the angle opposite phi is also equal to phi, so that stays constant. And if this angle stays constant, then the cotangent of this angle stays constant. So we can say now the cotangent of phi, okay, which is a constant, is going to be dr over r d theta, which is basically the adjacent over the opposite. So dr over r d theta is equal to a constant which we call a. So now, what I can do now, I can multiply both sides by d theta. So dr over r is equal to a d theta. So now I can integrate that. And when you integrate 1 over r dr, I get the natural logarithm of r is equal to a times theta. Now there's a constant which we add in here, but we're going to just minus that constant from this side and minus a portion of that, minus that constant from that other side, and the constant here, the new result, we'll just call that k. So now what can I do? I can raise both raise e to both sides. Okay, so what I've done is just raise e to those. Okay, so now e to the natural logarithm of r will give us r, and that is going to be now, in this case, e to the a times theta plus k, but whenever you add exponents, you're essentially multiplying. So I'll just call that new constant c. So basically now we just show that there is an exponential relation between the radius and the angle air theta, in that the radius is going to have an exponential relationship to the angle theta. So now, whether or not it spirals in or spirals out will be dependent upon the angle phi. If phi is less than 90 degrees, then we'll spiral in towards a spot. If it's greater than 90 degrees, it will spiral out. Okay, if phi is 0, it'll fly straight in. If it's 180 degrees, it'll fly straight out. If it's 90 degrees, it will be a circle. So anyway, that is all I have for now. I hope you find it very informative, and I would like to thank you very much for watching.